over to a session now for Boian Mitov. I'll see you in about 60 minutes. And Boian will be joining for the live Q&A as well, so see you soon.
Hello and welcome to the AI Code Camp. In this session, you will discover that Edge AI with Delphi is easier than you think. My name is Boian Mitov, the president of Mitov Software, and now let's dive in the session. AI has a long history. As soon as the first computers were created, people started exploring the possibilities of using them for artificial intelligence. In the early experiments, it was quickly discovered that while computers are very good at playing games, they do face considerable challenges when being faced with navigating a example environment, computer vision, and other tasks. Later in the early 80s, people came up with alternative ideas, creating expert systems using languages such as Prolog and Lisp. The idea of the expert systems was to take the knowledge of a particular person and try to implement all of this knowledge in the form of knowledge base. This, however, was discovered to be extremely limited form of AI, and this approach was quickly abandoned. Later, with the boom of computer gaming, a variety of game engine planning implementations of AI were created, and we can see examples of that in even such simple games as Pac-Man. In recent years, the classifiers have become a very popular form of AI. Early examples of such classifiers are spam filters and speech recognition. In the last few years, based largely on classifiers, a more modern AI has emerged, such as large language models and generative AI. Nowadays, when people are talking about AI, they tend to think about cloud-based AI such as ChatGPT as example. This is, of course, AI that requires internet connection and the computation is performed on somebody's servers. There is, however, another form of AI known as Edge AI. Edge AI executes on the edge of the internet, where the name comes from, or in essence, it's AI that will execute on your own system and does not require internet connection. The advantages are obvious. It will execute on your system. It doesn't require cloud or internet connection. It does not require you to pay for any services. It has low latency and low demand for internet bandwidth. It is secure since no data is transmitted to somebody else's system. And this way, privacy can be protected. Edge AI usually will be implemented in the form of classifiers. This is how a classifier works. A special module called Feature Extractor will take the data and extract from it features. The features are numeric values representing the data, and those values are sent to a classifier module. The classifier module detects and outputs conditions based on those features. Those conditions are often called classes. The classifier works in two modes: training and recognition mode. In training, we'll send data, the feature extractor will extract it and send the features to the classifier. In addition, we will specify the class or condition that corresponds to the features. And the classifier will learn that this condition matches the specific features. We will repeat this process until the classifier is trained. Once we have trained the classifier, we can switch to recognition mode. In this mode, again, the feature extractor will extract the features, and then, based on those features, using the existing training, the classifier will start recognizing and outputting the recognized conditions or classes. There are different types of classifiers, such as neural networks, including perceptron, naive or normal bias, hidden Markov model, kernel methods, support vector machine, k-nearest neighbor, mixture model, including Gaussian mixture model, decision tree, linear classifier, self-organizing maps, including growing self-organizing maps, and generative topographic maps. There are three different types of training for classifiers. Supervised training, where we train the classifier up front and then deploy already trained to be used for classification. Non-supervised training, where the classifier is deployed untrained and training happens as the classifier is being used. And finally, self-organizing classifiers. Those are classifiers that effectively train or organize themselves. AI classifiers have a vast number of applications. Here are only few examples: spam filtering, computer vision, OCR, speech recognition, diagnostic utilities, industrial control, investment, code formatting, gesture recognition, robotics, games, chatbots, text generation, image generation, and function approximation. For our first example, we will do function approximation. Imagine that you have measured xy values for some function and you have a certain number of those. We want to perform the function, however, we do not know the exact formula for the function. For this, we can use as example neural network and train it to effectively perform the function with certain approximation. For the project, I am using the neural network component included in Intelligence app. When training neural network, we also can use a variety of trainings. In this case, we will use a backpropagation training. For the backpropagation training, I have connected the training component to the neural network. Of course, we can add other trainings and also connect them to the neural network to train it in different ways. I will also use a scope component where I will display the data. Scope component is included in the Mitov software plot lab. Now let's take a look at our neural network. We'll configure it with one input and one output for the x and y values. We'll also add two hidden neuron layers, each with 6 neurons. Let's take a look at our neural network backpropagation training. Here we can specify the maximum number of iterations and what is our target or epsilon. We're trying to reduce the error below this value. Inside our button 1 click event, first I will create two matrices 26 by 1 samples. 26 is the number of training samples and 1 is the size of each individual sample. In this case, we have only one input x. A second matrix will contain the expected y result. Again, it will be samples by one size. Next, I will loop through the samples, populate the training data for the x and y, and for the x, I will do every fourth position, and for y, I will use an arbitrary function that I picked for this example. Instead of this function, you can use anything else, including measured data. And I will add the points to the first channel of the scope with the add xy point function, passing each element of the matrix. Next, I'll call the train method of the neural network backpropagation training, passing the two arrays. And finally, I will test the neural network training. I will create a test data buffer with size of one element, since each time we will be passing only single x value. I will loop to the 4 times number of samples to see some points between the samples, and I will populate the buffer with the x value and then try to predict for the y value by calling neural network predict, passing the test data buffer. In the neural network 1 on result event, we will populate the second channel of the scope to display the data. We will receive two parameters in our result. One is the features which were passed for this classification, and the result. Inside the result, we have results and other information, as example, how precise was the result. We'll pass the features, and the result results 0 for both, since we have only one x and corresponding y parameters, and we'll plot the point. Let's run our project and see how it performs. If we click on the Run button and give it a bit of time, we'll see the result of the training. Because the neural network starts randomized, we may get some areas of bad training. In this case, we can simply click on the Run button again, and most likely on the second run we'll get much better results. If we make the circles for the training bigger, we can easily see the points that we used for the training, with the red circles and the green circles representing the test points based on the approximation. Now let's do a bit more interesting example. In this project, we'll try to recognize faces. For the training and recognition, we'll use the AT&T training set of faces. The library consists of 10 images per person of 40 different people. For our training, for each person, we'll use the first 9 images to train the classifier, and then we'll use the 10th image to test how well the classifier performs. While the neural network that we use in the previous example is a great classifier and is widely used nowadays, it is very time-consuming to train neural networks. For this example, we will use a different type of classifier which, while not being as good as the neural network overall, has the advantage of being very fast to train. We will use radio basis function classifier, also known as RBF. In our code, we will declare few member variables or fields for the form. We'll explain their usage as we go through the code. For the button one click, which is the training, we'll create a bitmap. We'll create a features buffer. The images in the training set are 32 by 32 pixels, so we'll create a buffer with the size of 32 by 32. We will start populating the list view on the left side with the training faces images. We'll go through all 40 persons and we'll go to the first 9 faces. We'll load the bitmap with the corresponding file and we'll add the bitmap to the image list on the left side. Next, we'll create item for the list view. We'll set the item index to point to the last item in the image list, and we'll set caption corresponding to the specific person. Next, we'll get pointer to the pixels in the buffer, and we'll get right type of pointer to the features buffer. We'll loop through all of the pixels, which are 32 by 32, matching the buffer size. And for each pixel, we'll normalize it. Of course, the images are grayscale, so values for each pixel between 0 and 255, and assign them as floating point values in the buffer. Finally, for each of the faces, we'll pass the features buffer and the corresponding class, which is the number of the person. And we'll call the train method for the radio basis function network. Of course, then we'll end update for the list view and we'll release our already not needed bitmap. We'll also assign to a label indicating the number of so-called neurons in the RBF network that has been used during the training. Our recognition will be somewhat similar, again starting with creating a buffer and bitmap. We also will zero the total process count and error count member variables or fields, and we'll start iterating through each individual person. We'll read the recognition phase, which is the 10th phase. I have named it different way. And again, we'll add new item to the list view, set image index pointing to the end of the image list, get the pointers to the bitmap, pixels, and the features buffer, iterate through the pixels, again assigning normalized grayscale data, and finally call predict to see what will come back. Before we continue with this code, we will need to examine something else. For the radio-based function, if we go to events, on result, this event will be called every time we have recognition. We will increase the total count. If we fail to make any recognition, in this case our result count will be 0, and we'll report error. And we'll set this distance and result category. The category is the face identified. Since our face starts with 1, 0 will indicate completely unrecognized category. Distance is a value indicating the difference between the provided and the closest training face. In this case, that value has no meaning. If we have had recognition, we'll pick the most likely candidate, which is the first candidate in the result, and we'll take the category of the neuron that has been associated with the recognition. We'll get the distance for the result, the same first result. We'll compare whether the expected ID matches the recognition category. If not, we will also increase the error count, indicating that we have faulty recognition. Going back to our recognition code after the predict, now we'll evaluate what we have in these variables. If the result category is different than the face we are testing with, we'll indicate error, and if the category is 0, it's a face we cannot recognize. Otherwise, we indicate the face we have recognized, what we have expected, and the distance between the two. If we succeed, we'll just report that the recognition is correct, and we'll display how certain we are or what is effectively the distance. After everything is done and freeing the bitmap, we will display in a label the number of errors and what is the percentage of the recognition. Now let's run the project. If we click on the train button, you will see that literally within 1 to 2 seconds we have completed the training. Now let's try to recognize. We have succeeded to recognize with only 6 errors, which is 85% correct. That is quite impressive considering that we literally trained for 1 to 2 seconds and we trained with only 9 samples per face. We get pretty good results. This demonstrates the advantage of using a relatively simple type of classifier such as radio basis function classifier versus neural network.
We just demonstrated recognizing fixed size 32 by 32 pixel images of faces. In reality, however, when recognizing images, they're usually part of some bigger image, and we are trying to find where there are faces of certain people within that image. Often those faces or other items we try to recognize are rotated, which makes the recognition even more challenging. Mitov Software has developed Vision Lab. Vision Lab includes scanning component that can be used to scan image with certain X, Y, and rotation step. The scanned images then can be sent to the Intelligence Lab classifiers for classification. Let's take a look how the two libraries can work together.
Here is image with faces at different locations and rotations. We'll try to recognize this image. The Intelligence Lab classifiers are capable of saving and loading training. We can train, classify, save the training, and load it in completely different project to be used for recognition. In this project, we'll train a radio basis function network classifier and we will save the training. The simplest way to do recognition for faces at different places and rotation is to train with single orientation and then use the scanning component from the Vision Lab to scan locations and rotations. We'll start by setting the max influence field to 300 and inside the form create, we'll create a bitmap, features buffer similar to what we did in the last project, matching the size of the bitmap, 32 by 32 pixels. We'll go through all 40 faces, the 9 images for each of the faces, and again we'll assign the normalized values for each grayscale pixel to the features buffer, and we'll train with it. Finally, we can save our training to CTD file. Let's run the project. Within seconds, we have our training. And you can see that a new training file has just been created. Now let's use our training. For this, we'll use image generator for Vision Lab to provide the test image. If we double click on the component, we can open the picture editor and load image with faces at different locations and rotations. To scan the faces, we'll use the sampler component from Vision Lab. Both image gen, the sampler component, as well as the generic filters in these projects come from Vision Lab from Mitov software. Now let's take a brief look at the open wire diagram. Here, as you can see, our image generator, which is set to be clocked externally, so we can clock it only once, will send the image to this generic filter, and once the data is processed inside the filter, it will be sent to the image display. I'll explain why it is done this way when we look at the code. We have a separated chain which starts with generic filter 2, goes through the sampler, and then into generic filter 3. Let's take a look at the code now. To collect the information for each recognized location, I have created a record which indicates the recognized index of the face, the position, angle, and the distance or error of the recognition. We'll sort the detections in array list from Mitov runtime in Mitov containers list. We will also have two variables indicating the location and angle of the current processing position during the scanning. When the data arrives in our generic filter 1, the onProcessData event will be called. Here we'll start generic filter 2, we'll pass the arriving buffer, and then we'll stop the filter once the processing is done. The reason we're doing this is because we want the second chain to completely execute before we finish with this filter to send the data to the display, and we want to draw the necessary rectangles over the video frame. Once the recognition is done, will create a bitmap, will render the image buffer on the bitmap, will create the IGDI Plus graphics object. IGDI Plus is open source project maintained by Mitov Software, but it is also included in Mitov Runtime and all of the Mitov software libraries. We'll create, of course, font, and then we'll go through all the detections and we will display the rotated rectangles based on their position and angle. And we'll also display the recognized image class, or which person was detected by index. Finally, we'll release the graphics object, which is interfaced object, and nulling the interface, we'll release it, and we will render the bitmap into our output buffer, finally freeing the bitmap. Once this is done, the image will be rendered. Now let's take a look at what will happen in this chain. The image that we sent from generic filter 1 here will be sent to the sampler, and the sampler will scan it with rotations between 0 and 360 with step of 10 degrees and with specified default horizontal and vertical scan 10 pixels step. Finally, all this will be sent to generic filter 3. In the on-process event of generic filter 3, we will extract the location data provided by the sampler as custom data for the buffer. In essence, the sampler will provide a buffer and additional information informing that this buffer has location data. Then I'll assign the detected position and angle and our member variables or fields for the form. I will create a features buffer of 32 by 32 pixels because this is the size of the faces. Specify that the format is grayscale, and then, similar to what we did in the previous projects, assign the normalized pictures to the features buffer. Finally, I'll call the radial basis network predict, passing the features buffer. In the onResult event of the classifier, I'll check whether or not I have any recognition, and then I'll get the category or the index of the recognized face. Next, we'll check if at this position we have item of the same category, and we'll see if the new recognition has a smaller distance than the item at the location. If so, we'll delete the item and that location, and then, of course, at the end, the newly recognized location will be added. Otherwise, since we already know that we have item of this type at this location, we do not need to add. If we look back, now we can understand the open wire diagram. The image generator will send the data to the generic filter. The generic filter will send the data to this generic filter. The sampler will extract the samples and send to the generic filter 3. Generic filter 3 will call for each of those samples the classifier, and once the data is classified, the classifier in its onResult event will populate the member variable detections. Once all the detections are populated, this chain will finish. It will return to this generic filter. Here all the detections will be rendered on top of the frame, and the completed frame with the detections will be sent to the image display. Now we can run the application. And we can see the recognized faces, locations, and rotations, as well as the class. Similar to other classifiers, the radial basis function network classifier can improve its recognition if it is trained repeatedly. To demonstrate this, we'll modify our training code. Here, in the onFormCreate, we'll modify the code to repeat 3 times the training. The rest of the code will remain the same. Let's run the project. This will create new training. Now we'll go to our previous project, double-click on the radial basis function network, and select the newly created file. As you can see, this file is bigger as it contains bigger training. Let's run the project. It can take up to a minute to start the project as we have much bigger training. As you can see, now we have many more locations and faces recognized. So obviously the repeated training improved the recognition considerably. Be aware that repeated training can also result in overtraining the classifier, which could lead to worsening results. It takes some experimentation to find a good balance between too little and too much training. The radial base function classifier in Intelligence Lab, as well as many of the other classifiers in the library, has a very useful feature. It can be trained not only with features, but also associated weights with each feature. If that associated weight is set to 0, we can completely mask that specific feature. This is extremely useful if we want to mask areas in case of rotation, as example, or areas around the face, areas that are part of the background. We'll use this functionality to train with rotated faces. Now, let's see how we can use this feature of the classifier. Here, we'll both rotate the images and we'll also resize them to optimize the training. This will improve the performance of the classifier, and it may also, oddly enough, actually result in better recognition as the classifier starts to look more at general features than very specific pixels. So we'll have 2 chains. One will process our image, the other one will process the mask. This will start with image generator set for external clocking, so we can clock it from code. This generator will contain the mask with the black area masking the part that we want to ignore and the white area covering the image. In this case, we just want to mask the whole square of the face, but in some cases we want to mask even more specific details. Here is the code. We'll start with declaring two member variables in the form. One will be the category we are training for, and the other is a mask image to use to mask the rotated faces. In the bottom, we create a bitmap. We start the generic filter 1. We prepare image buffer 32 by 32 pixels, matching the size of the training images. And again, similar to the previous trainings, we iterate through 9 images for each of the 40 faces, although in this case we'll start not with 1 but with 0. Here is another trick. We'll train not only for the faces but also for the background. We'll use 0 to be the background, and we'll set, in case of background, category of -1. We'll also have a label where in the caption we'll display the progress. The category, of course, is set to the specific face. If this is not background, we'll load bitmap image from file and we'll assign the bitmap to the image buffer. We'll set the image buffer to grayscale, and now we'll start training for the rotations. We'll set both rotations to the same angle. The step will be 10 degrees between 0 and 360. So these two rotations. In the meantime, our resize will be fixed to reduce the size to 14 by 14 pixels. And once the angle is assigned, we'll first pump the image generator. This will start this chain. The image will be pumped, rotated, resized to 14 by 14 pixels, and sent to generic filter 3. Here, inside the unprocessed data, the input buffer format will be set to grayscale, and we'll assign it to the mask image, right here. Now we have both mask image assigned as well as corresponding category. Both of the member variables are assigned, albeit at different places. That will complete this chain, and we can continue with the code in the bottom. Once this pump code is completed, we'll send the image buffer with the face, the same image that we loaded from file. We'll send it to the generic filter 1. Again, the image will be rotated, displayed on the display so we can monitor the progress, resized, and sent to the generic filter 2. Here, inside the unprocessed data, we will similarly set the format to grayscale, convert it to features buffer of bytes, convert the mask image to features binary buffer of bytes, and train the classifier with the features and the masks as well as the category that we assigned right here. At this point, this chain is also completed. We will allow the application to process the messages so we can update the user interface, and we'll continue with the loop. Once all this is done, we'll send a stop command to generic filter 1, and we'll save our training to a CTD file. Now let's run the project. If I click on the train button, the training will start. This will take a while since we have to iterate through a lot of images and rotations. The training is completed. Now that we have our training, we can use it. I have created a project similar to the one we used before for the face recognitions. Let's load the training in our classifier. Double-click on it. Select the mask rotated face training and click Open. This will load the training. In this project, unlike in the previous one, we will not rotate, so we can set the min and max rotation to be 0, so images will not be rotated. We'll also take a bit bigger sample size, 46 by 46 size. This is because we have surrounding mask. We want additional pixels for the mask. We will also, once we get the data from the sampler, we'll resize it to 14 by 14, which will match the training we did for the faces. So let's explore the open wire diagram. We'll use the image generator with the same test faces as before. We'll set it to external clocking, so we can clock it in form create. We'll change the format to grayscale and send it to generic filter 1. In the onStart event of generic filter 1, we'll start generic filter 3 with the same width and height as filter 1 and a frame delay, identical to the one we have. In onProcess data, we'll send the data from generic filter 1 to generic filter 2, the same we started. And here, once the data is processed, similar to the other project, we'll render the information using IGDI Plus of the recognized faces and locations. For details, please watch the section we did before, except since we don't have angle, here the code is a bit simpler. We simply draw rectangles and display the recognized class or face index. Once this is done, the resulting image will be sent to the display. In the second chain, we already covered it. We resample, resize, and the data will be sent to generic filter 3, where we will perform the recognition. Similar to the other project, we extract the sampler location data. We assign it to the detected position member variable, again identical to the previous project. We also have detections, array list of detections. The detections are similar, except here is simpler. We do not have angle, and we don't have to remove detections at the same location. We can simply add the new detection at the same place, since we are not going to do the rotations. This is the entire code, aside of a little housekeeping, such as the detection constructor, which is simple enough. Let's run the code. The recognition will take a while. And now you can see all of the detected faces. As you can see, in this case, we do not have any rotation, and the recognition is indeed much better than the alternative approach. It also executed noticeably faster. This is pretty good considering that we did only single pass of training. We have very impressive results indeed.
The next interesting aspect of using classifiers is that the feature extractor in front of the classifier has effect on the recognition. If you use more relevant features to fit the classifier, you will get a better prediction.
To demonstrate this, we will implement a simple OCR type application. We will again use radio base function network classifier, and for the training,
we will use training images which are provided in the form of characters, spaces, pulses, and sharps. Sharps represent color of black, pulses color of gray, and spaces white. The training set is provided by the US Postal Service for testing character recognitions of numbers. They also provide corresponding file with labels for each image. The images are hand-scribbled.
in this project, we will load the images in two image lists. For this, we'll have to convert them from the text files into images. We'll do this in the form create event. For this, we'll use a couple of helper functions. In this function, we'll convert the text into image list. I will not go into great details of the code here, as it has nothing to do with artificial intelligence. You can study it yourself. However, all we do is we load the file, create bitmap, and then we go through all of the lines in the file, and we extract the pixels as displayed with those symbols, and as we already mentioned, plus is gray and sharp is black, while everything else, which in this case is space, is considered white. Effectively, we'll have a grayscale image. Once we have done that, we add the image to the image list. We'll also use a similar function to load from file all the labels, which are the different classes. Classes are also sometimes called labels. Here are the labels loaded in the form of image buffer, converting string to integers and assigning it to a real buffer, which will convert them to floating point. So we will populate the training image list with the training images, the training labels with the training labels file. We'll populate the list view. Let's take a look at this function. It is very simple. We'll iterate through the list view, add items, and set their image index. The reason I use two separated for loops is that, oddly enough, for some weird reason in VCL, it works faster than assigning the items and immediately setting the index. It's a trick that I have discovered. And after that, we will assign the list view labels, which simply will be going through all of the items and assigning their captions. We'll do the same for the test list view. Training and test list view. And of course we have training and test image lists, which we have populated here. That's all the necessary setup. Now inside our train and classify event, we'll extract the features. In this case, for our first test, the features will be simply the pixels in the image. So I will go through the image list, extract a bitmap, and I'll call extract features. For the bitmap, as you can see, we're simply iterating through all of the pixels, and if the pixel is different than white, we're setting it to 1. If it is white, 0. So we're effectively converting the grayscale to non-white color for simplicity. This will produce a real buffer of the size of the pixels of the image with multiple height. We'll append this to the results, and at the end we'll have an array of such real buffers. This is our training data. We also already populated training labels, which happens to be also real buffer. Now we will iterate to the training data, and for each training data and training labels in the two effective collections, we'll train the neural network with features and corresponding labels or classes. Once again, the features are just the pixels 0 or 1, white or non-white. Once this is done, we'll do something similar for our test image list. We'll extract the features again in the form of matrix, and then we'll iterate through the image list, and for each image, since we have the same number of rows in the matrix, we'll call predict for the neural network. In our own result for the classifier, in case we have 0 recognitions for that item, we will simply assign result -1. Otherwise, we'll assign the category, and this will be assigned to this member variable result. Once the prediction is done in the bottom, we'll compare the expected result in the test labels with the result we receive from the recognition. And if they are not the same, we'll display error with additional information. Otherwise, we'll display what we have recognized. Finally, once when we're done going through all of the images, we'll display the statistics of our recognition, percentage correct, number of errors, and everything else. Let's run the project and see how it works. Here are our images. Let's try to train and classify them. As you can see, we have 109 errors out of 1000 images, which is 89.1% correct recognition. This is not bad, considering that we did a single pass with just pixels as information. We can improve upon that, however. If we pay attention to the images, we'll discover that 8, as example, has 2 surrounded areas. This top one and this bottom one, as well as the area outside. Those regions are called closed spaces. As example, 8 has 2 inside and 1 outside. 9 has 1 closed space inside, 1 outside, the same as 0. And 6. By using the number of closed spaces as features, we can try to improve our recognition. To find such closed spaces, we will use another component from Vision Lab. This component is called Connected Components. Connected Components is another way of saying closed contours or surrounded spaces, effectively. This project is almost identical to the previous one, however, there are few changes to allow for the counting of the closed spaces. Let's take a look at the open wire diagram first. We have generic filter and connected components from Vision Lab. The generic filter will send the data to the connected components. So far, nothing complex. Let's take a look at the code. First of all, we'll have new member variable. I have decided to call it count zones, which will be the surrounded areas, effectively. The extract image features is almost identical with a couple of exceptions. We add one more element to the resulting real buffer, which will contain the count zones. Once the buffer is prepared from the image, the same image that we use to extract the pixels will be sent to generic filter 1. First we will issue start command, send the data with a buffer created from the image, and finally we'll send a stop command. Let's see what will happen at this point before we continue. The generic filter will send the data to the connected components, and the connected components on its own components event will receive the count of components, and making sure that it is no less than 0, we'll set the count -1 to the count zones, making sure that just in case we have 0 count, we don't set it to negative value. After all this is done, we have our count zones. We divide it by 5 to semi-normalize it and make it similar to the rest of the pixels, and finally assign it to the last element of the real buffer result. That's all we need to do here. The rest of the code is absolutely identical to our previous example. Let's run the code. If we click on the Train and Classify button, we'll see that now we have one less errors. We have 108 errors versus 109, and our percentage has improved from 89.1 to 89.2. This may not sound that impressive, but everything helps. And this is a simple example of how just adding one more relevant feature can improve our recognition. As you have seen, classifiers are computationally intensive, and the processing sometimes can take considerable amount of time. There are ways, however, to improve the performance. We can use parallel execution on multiple CPUs or cores, execute on GPU, execute on TPU or tensor processing unit, or use distributed execution on multiple systems. And finally, we can even use field programmable gate arrays, FPGAs. The Intelligence Lab classifiers, as well as many of the Vision and Video Lab components, allow you to specify how the processing will be executed. Here, if we expand Processing, we can select the engines and click on the period button. And here we can select parallel execution as example. We can even specify how many threads will be used and what priority will be used for the threads. Alternatively, we can select GPU processing and we can select the GPU platform that will execute the classifier within the GPU. This allows us to speed up the processing considerably. So, what we have learned? More relevant features result in better prediction. Classifiers tend to require a lot of computational power. And finally, it is important to remember that selecting a good training set is very important. So spend a lot of time preparing and making sure that the training set is of high quality. Now that you have discovered how you can implement Edge AI with Delphi, here are some examples of what you can use it for. Self-driving cars, drones, and robots, since internet connection very often is not option at all. Similarly, industrial automation and security systems as well as face recognition often have to work completely offline. And finally, for security reasons, they're a good choice for things like spam filtering and fraud detection as example. As you have seen, by using Intelligence Lab, implementing Edge AI with Delphi is relatively simple. Delphi, as a native cross-platform high-performance compiler, is very well fit for Edge AI. Intelligence Lab makes implementing Edge AI fairly simple on Windows, Mac, Linux, iOS, and Android. Combining it with Vision Lab, Video Lab, and Audio Lab allows for implementing computer vision and speech recognition types of Edge AI. Combining it with Visuino, it allows for IoT and embedded devices to be controlled with Edge AI. The built-in, parallel, and GPU execution support in the libraries allows for high-performance Edge AI implementations. Finally, a few words on the business of AI. In terms of coding, there is, of course, a constant demand for better types of classifiers and implementations of existing classifiers. The same applies for the feature extractors. In addition, not only the software, but also the training is intellectual property and a product of its own. Even the training sets are themselves a product and are considered intellectual property. Once again, my name is Boian Mitov, the president of Mitov Software, and here are the Mitov software products: Video Lab, a video processing library; Audio Lab, audio processing library; Signal Lab, digital signal processing library; Vision Lab, computer vision library; Plot Lab, data visualization library; Instrument Lab, visual instrumentation library; Intelligence Lab, artificial intelligence library; Logic Lab, Boolean Logic Library, Animation Lab, Universal Animation Library, Communication Lab, Serial and TCP Communication Library, including MQTT, Control Lab, Industrial Control SCADA type of library, including protocols such as Modbus and OPC, Visual Live Binding, Universal Visual Live Binding Library, Mitov Runtime, a free Delphi library, OpenWire Studio, a graphical development environment for Windows, and Visuino graphical development environment for Arduino. Mitov software also maintains the following open source libraries: OpenWire and iGDI+, a Delphi-friendly GDI+ library. Thank you for watching, and now it's time for questions and answers.
Well, that was mind-blowing. And it was a longer presentation, but that's exactly what we wanted. Because Boian, I've said this before, and he actually thanked me yesterday after I said he is one of the smartest guys I know. And the good news is he's live with us today. Hi, Boian.
Hello, everyone.
So, a lot of very positive comments about your presentation. I mean, Maxi Donkey is clearly a fan. I said this before, Maxi Donkey knows what he's talking about because he produces a lot of AI stuff. I must stop, move my leg around because I make it look like I'm in the middle of an earthquake, which doesn't happen very often in Texas. Bit more dodgy for you in California, but there you go. But so many comments and things like that. So let me have a look at what was said, because I starred some of the. I mean, I didn't. Some of the questions I didn't even understand the question, let alone know what the answer was. So, I like this one, for example. Have you tried to study the topology of the latent space created for your training?
I have not. Yeah, I agree. Again, when I started like 15 years ago, nobody was doing AI. I was one of the very few idiots out there that were doing AI and implementing AI functionality. And nowadays, there is so much. I mean, even the lingo from 15 years ago, it has completely changed, right? So things are just changing, and there are new researches every day, and there is no way for me to keep up with all of that, considering that, again, I do a fair amount of AI, but I do so many other things. I have to cover all of them.
Yeah,
and I am unable to cover everything.
Your last slide there pretty much made it obvious how much you do actually do, which is a ton of stuff. I'm going to put this down here as well. For those that aren't very competent at scanning QR codes, and I know some people don't manage to do that for whatever reason, but the QR code is there. It will take you to there, so it's the same place as the heading down there. But mitov.com or Mitov, but it's Mitov because now I've had Boian on enough times that I've heard him say his surname, and it's gone in now. I remember Mitov, not Mitov. So there you go. But you've always been very kind about not calling me out on that.
No.
So lots and lots of things. Richard Maley said this is very impressive, and I absolutely agree. If anybody goes to Mitov software, if you go to mitov.com, it's literally how it's spelled, mitov.com. Go there and you will find a component for anything you could imagine. Absolutely everything. Communications, MQTT, which is my favorite comms protocol for Internet of Things and stuff like that. Intelligence, signal processing, you name it, there is a component there. And that is only the start of it. Those are just the Delphi bits and bobs. So there are hundreds of libraries there. But he also does Visuino. which is a whole IDE for the Arduino things. You've seen me do Internet of Things before with these little boards, and I haven't got one near me, but little cubes with LEDs on. Jim McKeith is doing something with. He showed me a message, a photo of a board he's got like that long, about 2 or 3 feet long, with loads of LEDs in it, and he said, I'm making it do stuff. He never did explain what he did, but you never know with Jim because he's pretty crazy as well. But he's also, Jim has always been a big fan of your stuff as well. So
Thank you.
You're a great guy. You are without doubt one of the smartest people I know, and I say this so many times to some of our guests because I only get on the best. But you are, you're a smart guy, and you're a nice guy with it as well. Couple of questions. So this one was you did actually answer this in the questions, but
Sure.
I want to call it out. And we, by the way, Daniel Fernandez is on after this, and we're going to start his session a bit late. He'll be fine. His video is not that long, and he's not turned up yet for the Q&A. So, the one question which you did answer, but I'll call it out again: the face recognition demo that you showed, can it detect other faces too, or only the one input face?
Yeah, so the way basically you train it to recognize specific people, and it can recognize the same person within other images. Again, even in the demo, the image with which I tested was not one of the images I used for the training, obviously, right? So if I recall correctly, it was 40 faces, 10 images per face. I used 9 images to train, and I used the 10th image to test, since it's a very minuscule set, right? So the answer is yes, it's going to recognize in those faces. Obviously, any other person, it most likely is not going to recognize because it's not one of the faces we have trained for.
Yeah, and the thing as well, I hope everybody's understood this, but I'm sure they have. But this is all offline as well. This is not using some large language model or anything like this. It's all about doing it yourself on the edge.
Yes.
And
yes.
And that's the key thing.
Yeah. Yeah. Again, when I implemented all of this, actually, a lot of this stuff, again, I keep expanding it and improving it. But all of these libraries were available as early as 13 years ago. So some of the demos, not all of them, but some of the demos, they were demos and projects that I have done even 13 years ago. And at that time, there was no cloud, obviously.
It didn't exist.
Yeah, it didn't exist. So everything was working offline back then, and everything is working offline now. And that was asked questions, so I will use the opportunity to answer. The demos I did, they were all done on the CPU, and then I show quickly how, and they were executed on single thread, by the way. And then I showed very quickly and briefly how you can switch to execute in parallel on multiple threads, and how you can select the execution to be on GPU. So up to you, right? So
yeah, and that was one thing that I wanted to get in this week as well of events, because I had Yilmaz on as well, and I'm sure you know Yilmaz, and Yilmaz has been doing AI long before AI was the hot topic, and so were you. As you said, you've been doing it for about 15 years. Yilmaz has been doing it for maybe even longer than that, I think. And he's a professor and he's a smart guy, but he's another one of these people. Sometimes people asking questions, I don't understand the question and I don't understand the answer either. But at least I know it's cool, That's I don't. I've always said to people, just because I'm fairly well known, most people know my face in the Delphi industry now. It doesn't mean to say I'm special. I'd make it very clear I'm an okay developer. I mean, they wouldn't give me the job if I was no good. But I'm not. I don't claim to be a rocket scientist or extremely talented or anything. I'm a developer. I'm good at it, but I'm not like the best in the world. And that's the important thing, because I don't want people to see me doing something and go, oh, I could never do that. All of you can do these things. And if you use Boian's libraries and things like that and follow along with these examples, you too could have your own AI locally. Why pay, thousands of dollars a year to Google or whoever, when you can do some, not all of the things, okay, but some of the things can be done. There are certain narrow use cases that can be done with your components. I would say that's true. Yeah, I mean,
Yes. By the way, one important thing is, and it was kind of mentioned, the libraries are, this particular library is cross-platform. So while not all of my components across all the libraries are cross-platform yet, the Intelligence Lab is fully cross-platform. So the same examples that I show, pretty much you can run them on Android as example. And by the way, just to use the opportunity to mention it, well, I said that not all components are yet ported. In the next version, almost all of them are going to be actually ported. I'm making a very big push to port to as much cross-platform as possible, including video processing, audio processing, all of that stuff. And big part of it is already working cross-platform as first iteration. So by the end of the year, it's highly likely that the video and audio components that were not yet ported, because some were, they all will be fully ported as cross-platform. Just something to mention here.
I mean, if you ask OpenAI about me, it describes me as a prolific programmer and software developer and a writer and things like that. But you're prolific because you churn out code like some kind of machine. I swear you're actually really a robot, or you've got clones. There's some way you're doing this because see, I knew it. I was right. But you produce so much stuff. It's ridiculous, really. It makes the rest of us look like slackers. So there you go. All right. Well, look, I think we covered most of it. I do need to go on to Daniel's session as well. But Boian, thank you so much.
Thank you.
Every time I say this, for every hour-long video that people see, there's a lot more hours gone on behind the scenes and a lot of effort. You're very good at organising things. We nearly messed up your session as well. We told you Monday, then we told you Tuesday.
No worries.
But I think we got it right this time, and there were plenty of people watching live, so you're good. All right, thanks a lot, Boian.
Thank you.
Thanks. Okay, so that was Boian Mitov, and you see his website there at Mitov Software, and I thoroughly recommend going to have a look, even if you decide not to have his components. His components, by the way, his components are very cost effective. I don't want to use the word cheap, but the price for them is actually very reasonable. And Jim McKeith used to say he was crazy because he should charge more. But what he does is he aims for popularity in that. He wants his stuff to be used. So go along and check it out at mitov.com, which is that one there, or scan this QR code and it'll take you to there. It's the same thing. But thanks to Boian.